Okay, so let's go through it. So if this reaction is faster, note that IO3 minus reacts with HSO3 minus to produce I minus. So this reaction occurs fast. If reaction 2 is slow, the I minus reacts with IO3 minus, but if this reaction is slow, will this reaction occur compared to reaction 1? No. So if this reaction 2 does not occur, will I2 be produced? So if I2 won't be produced, will the solution turn blue? No. Let's do the second part. Let's say that reaction 2 is faster than reaction 1. That means that as soon as I minus is produced, it will react with IO3 minus because this reaction is faster than that one. So as soon as reaction 2 occurs, what will be produced? Yeah, I2. And as soon as the I2 is produced, what color does the solution turn? So which reaction is faster, reaction 1 or reaction 2?
1.
Okay, so note again that when IO3 minus is mixed with HSO3 minus, these are two colorless solutions. When they're mixed together, the solution remains colorless. After some period of time, it will turn blue. Okay, so as soon as these two solutions are mixed together, it does not immediately turn blue. Okay, so it takes some time period for that solution to turn blue. Okay. Okay, so again, is reaction 1 faster than reaction 2, or is reaction 2 faster than reaction 1? Okay, so who says reaction 1 is faster? Who says reaction 2 is faster? If you notice, a few of you changed your mind. You went from reaction 2 to 1 and 1 to 2. Okay, so let me talk one more time. Let's assume reaction 1 is faster. So the IO3 minus reacts with HSO3 minus. That produces iodine, I minus. Okay? So as soon as the I minus is produced, it can react with IO3 minus, but if reaction 1 is faster, will reaction 2 occur or will reaction 1 occur based on the substances present in this solution? Okay, so if reaction 1 is faster than reaction 2, which one will occur? Reaction 1 or reaction 2? Okay, so if reaction 1 occurs, that means that all of the reactants will be reacted, which produces I minus. So as soon as all of the HSO3 minus has reacted, in other words, there's no more left, then the I minus which is produced can react with any IO3 minus which is left over to produce I2, and as soon as the I2 forms, what color does the solution turn? Blue. Okay? Let's assume that reaction 2 is faster. So reaction 1 occurs and produces a little bit of I minus. The I minus can react with the IO3 minus, which is originally present in the solution. If this reaction is faster than that one, what will be produced? Yeah, it will produce I2, and then the solution will turn blue. So if reaction 2 is faster than reaction 1, this solution should turn blue, and when should it turn blue? Yeah, right away. So which reaction is faster, reaction 1 or reaction 2? So who says reaction 1 is faster? Who says reaction 2 is faster? So yeah, it turns out the reaction 1 is faster. Okay. So again, these are the three reactions that you'll look at in this iodine clock reaction. And what you'll do is you're going to change the concentration of either IO3 minus or HSO3 minus and figure out how long it takes. You actually measure how long it takes for the solution to turn blue. And that's how you can determine the rate of this reaction. Okay. There's another question down here. In reaction 1, which reactant, IO3 minus or HSO3 minus, must be the limiting reactant for this solution to turn blue? Okay, so which reactant must be the limiting reactant? Yeah, so it's either going to be HSO3 minus or the IO3 minus. Of course, the easiest way to figure this out is just take a quarter out of your pocket. And heads, it's IO3 minus, tails, it's... But then, you want your odds to be better than 50-50, right? Because you just want to guess. Okay, so, whether it's 51-49 is better than 50-50. So, which reactant must be the limiting reactant in the reaction 1? The IO3 minus or the HSO3 minus? HSO3 minus. So who says that the limiting reactant must be IO3 minus? Who says it must be HSO3 minus? Yes, so you're right, it has to be HSO3 minus. So again, if we go back to this picture here, note that if HSO3 minus is the limiting reactant, and as soon as all of this has reacted, there will be leftover IO3 minus. Leftover IO3 minus reacts with what? Yeah, the I minus, that's reaction 2. So the I minus reacts with the leftover IO3 minus. That's going to produce I2, and that's going to make the solution turn blue. Okay, so in this lab, what you'll do is you look at reaction 1. So these are going to be the concentrations. You'll actually do several reactions. So you'll take 10 milliliters of IO3 minus. The concentration of this substance is 0.02 molar. Then you take 10 mils of a 0.002 molar of HSO3 minus. You'll mix them together. We'll do this calculation in the lab. This is a stoichiometry calculation. The rate law is described by this equation. So the rate is equal to the rate of rate of disappearance of IO3 minus with respect to time. That's equal to the rate constant K times IO3 minus to the X power times the HSO3 minus to the Y power. What you'll do in lab is you're going to measure the rate of this reaction by measuring the time. We'll also figure out how to figure out the change in concentration of IO3 minus. Okay? Then we'll be able to figure out, based on the rate of this reaction, and these concentrations, what X and Y are going to be. Okay, so we'll figure out what the order of the reaction is based on the experiment. And then delta T is the time for the solution to turn blue once you mix those two solutions together. So how can we figure out how to do this experiment? So let's take a look at the next slide. So one way to do this is by doing these two steps. So in step 1, what you want to do is you want to change the concentration of one reactant, keep the other reactant concentration constant, and then measure the rate. And then you do several different experiments. Then in step 2, you'll compare the rate with the change in concentration to determine the order of the reaction with respect to each reactant, and then calculate the rate constant K. Okay, so let me just give you an example of how you would do this. And then we'll do a few problems from the textbook. Okay, so let's say you have this reaction. You have A plus B going to products. And then we can represent the rate law by the following equation. So here's our rate law. So the rate is equal to K times A to the X power times B to the Y power. Okay, if you don't want to use x and y for your exponent, use whatever. Use your favorite exponents. You know, a, b, c, d. Okay, y and z. Whatever you want to try. Okay, so let's say you do a few experiments. So let's put a table here with experiment 1, 2, and 3. And here's the concentration of A and B in the spirit. Then we'll also figure what the rate of this reaction is. Okay, so let's just say that in experiment 1, the concentration of A is 1, the concentration of B is 1. Let's say the rate is 10. Okay, so we won't put any units in here right now. In experiment 2, okay, so let's follow step 1. We're going to change the concentration of one reactant, keep the other reactant concentration the same. Okay, so let's keep this one the same, and we'll change the reactant concentration of B to 2. We're going to measure the rate for experiment 2. Okay, see if it changes. So let's say that the rate goes from 10 to 20. Note that if we compare experiment 1 to experiment 2, we can figure out how the change in concentration of B affects the rate. So this tells us, by comparing 1 and 2, we can figure out what y is. Okay. So for the third experiment, let's keep the concentration of reactant B the same as was in experiment 1, and we'll change the concentration of A, and we'll see what happens to the rate. Okay, so let's say it's 10. Okay, so we did 3 experiments. We kept one reactant concentration the same, we changed the other one, we measured the rate. So in step 2, we can compare the rate with the change in concentration and see what happens. Okay, so let's do that here. Okay, so let's do this. Let's take a look at the rate of experiment 2 compared to the rate of experiment 1. Now the rate of experiment 2, that's equal to